Morning. Okay, so till all students join, will revise once yesterday's class. So yesterday I have discussed a very important uh, topic, avalanche photodiode. Okay, and in avalanche photodiode, these photodetectors are generally prepared with semiconductor materials, and main intention of photodetector is detection of light. So in that photodiodes are there, avalanche photodiode is there, and the PIN diode is there. Okay. So in avalanche photodiode, the main advantage of avalanche photodiode is it detects low level, low intensity photo. That is low intensity light. Okay. So how it is constructed? Yesterday we discussed it. Different layers, different doping levels, doping with different doping concentrations in silicon, it is constructed. Okay, and here this is important region P plus and N plus and P just acts as P and diode. And here this total thing is connected in reverse bias. When it is connected in reverse bias, generally what happens at this region, higher, because reverse bias, potential barrier will be more. That is, higher electric fields are present. Okay, when light is incident on this region, on the photodiode or intrinsic region or pi region, the incidence of photon creates an electron hole pair. When photon is incident on it, electron hole pair will be created here. This electron hole is, or electron and hole separately driven in the field direction and opposite to the field according to its charge polarity. This electron, whatever the electron hole that is generated due to incidence of photon, this electron, okay, hits the lattice, and from that one electron is removed. Ionization takes place. And again, in that situation, whatever the electron hole created due to ionization is called secondary electron hole pairs. These are primary. Due to incidence of photon, the electron hole pair formed is primary electron hole pair. Okay, and these primary electron hole pair incident with the lattice atoms, and there it results in creation of secondary electron hole pairs. Those secondary hole pairs again collide with elastically, collide with crystal. Finally, multiplication of electron hole pairs takes place so that then electrons enter into that circuit again. obviously we can see the current flow. When photon is incident on it, then you can see current flow in the circuit. You are seeing current flow in the sense photon is incident, it is detected. Low level intensity, low intensity light is detected. Okay, so that variation also we discussed it, how it happens, how electric field profile also we discussed. Now coming to pin diode, PIN diode, that is almost functioning is same, principle is same, but small variation is there. Instead of having this different variations in doping levels, simply we take a P intrinsic region and N. Okay, see here. Right. Now in this PIN, this is P-type material, right? And intrinsic region here we take, this is P-type, this is intrinsic region, this is N-type material. Okay, when photon is incident on it, in the intrinsic region, when photon is incident, here electron, when this is P-type, this is N-type, in intrinsic region, electron photon is incident, then electron hole pair will be created, right? And because we apply, again here also we apply reverse bias, as in case of photo, whatever the photodiode you take, we have to apply reverse bias. So these generated electron and the holes, according to their polarity, they move in the field. Okay, finally light is detected. Here, impact ionization, which is important concept in photodiode, does not take place. Impact ionization will not be taken place here. Right. One more important point in this, because this depletion region is, or intrinsic region, depletion region is higher, wider, there is a possibility of um, possibility of flow of electrons due to minority charge carriers. Clear? Minority charge carriers will be there. Okay. Due to that, current flows in the circuit. That is dark current it is called. So dark current flows. Even though light is not incident on it, it may in the circuit some magnitude of current will be seen. That is due to these minority charge carriers, because this intrinsic region is wider. Okay, and that is called dark current. Right. When photon is incident, same phenomena. Electron hole pair will be created, and electron moves according to its polarity towards higher potential, and it is lower potential. You can see the current flow, additional excessive current flow in the circuit. Clear? So if you see the graph, see one, if you see it, see how the electric field is varying. Electric field profile. We are taking electric field on this axis and along the length of the material. Okay, so the electric field is increasing in that region, and finally it is absorbing. Right, this is recombination region. This is absorption region. Absorption region. This is recombination or gain recombination region. Okay, here, but whereas in case of avalanche photodiode, if you see, if you can remember, see this at the region where the PN diode in the first part, N plus and P, at that barrier region, maximum gain takes place in the pi region, total absorption. In the pi region, absorption will be taking place, and maximum gain we maximum gain or maximum electric field will be taken place in the PN, that region, forbidden region. But in case of PN, this PIN diode, here maximum recombination in the same, in the intrinsic region itself, total absorption is taking place, right? So this is the electric field profile of PIN diode. Let us see the variation of how this current varies with the um, intensity of light. Okay, and if you see the graph, that is very important in case of P&A. That's what in the lab we can do it. We can study VI characteristics of this photon, this PIN diode. See, in this PIN diode, if you see the graph, see here, we are taking, if you draw a graph, the current will be in milliamps and voltage in volts, VI characteristics, output characteristics. So initially you can find that before incident of any light, any photon on the material, on the PIN diode, then find a curve like this. Are you able to see it? See, the I has a constant value at minimum voltages, initial value. Okay, minimum reverse voltages, reverse bias voltage. So smaller current, small magnitude, lower magnitude currents are there. This is dark current. Dark current. This is dark current due to dark current. How we get dark current? Due to minority charge carriers, because the intrinsic region is wider, we get dark currents. When light is incident on it. So one more doubt. Even in the avalanche photodiode, we have wider depletion region due to reverse bias. Even there is current flows due to minor. Okay, we'll discuss that. I understood. Now, when this is before application of before incident of any photon, when light is made to incident, slowly current increases. This is some intensity of light, and further increase of intensity of light, current increases because electron hole pairs are generated. Here intensity is gradually increases. When intensity is increased, obviously more number of electron hole pairs will be generated, that you can see. So in this way you can detect the light. Okay, in many transmission these things, when if you want to detect a light, and if you want to convert photo energy, light energy into electrical energy, we use PIN detectors. One is photodiode, one is avalanche photodiode, another is PIN diode. Okay, now in avalanche photodiode, there also these minority charge carriers will be present, but we made arrangements such that these charge carriers will not cross the depletion region. If you remember yesterday's class, if you remember the photo, see this here. This is wider, of course. Minority charge carriers are present. Okay. And these minority charge carriers to cross this depletion region. This region. That is the reason. That's why there we don't get any dark current. That's why we use that photo detector, avalanche photodiode, for to measure the low intensity photons, low intensity optical signals. Clear? So this is the story of PIN diode. Right now, we'll discuss one more important thing. In previous class, we have discussed about radiative and non-radiative recombination. See, in these things, if you have any doubts, you can ask me in the chat, or you can ask me in WhatsApp chat. Okay. And if you have any doubts, you can personally um, call or personally can message. We'll discuss that. Okay. Now, once for 2-3 minutes again, we'll revise this PI and we'll switch over to another topic. So, what is PIN diode? It is a photodetector. What is the material used to prepare PIN diode? It is the semiconductor material, right? And what is the bias that is applied in the PIN diode? Reverse bias. Okay. Next point is what is the principle? The principle is same: conversion of photo optical signals into electrical signals. Okay. Conversion of electrical signals into optical signals into electrical signal. Right. Initially, the PN diode has P. We take germanium PN diodes, or their silicon, or their gallium arsenide, or their gallium arsenide phosphide. Different combinations are there. Say silicon PN diode. If you take silicon, is taken at one end. P pentavalent or dopant will make by trivalent atoms or dopant becomes P type, and another end pentavalent atoms or dopant becomes N type. So finally it is PIN diode, right? In PIN diode, the bias applied is reverse bias. Is it clear? In PIN diode, the bias applied is reverse bias. What is the principle in PIN diode? It converts optical signal into electrical signal. Okay, converts optical signal into electrical signal. This is the basic principle in PIN diode. And what happens when light is incident on PIN diode? In that, what happens actually? What is I intrinsic region? Okay, what happens when light is incident on PIN diode? That photon, that light generates or creates electron hole pair in the PIN diode, right? So generated electron hole pair, according to their polarity, electron and hole, they move in the field direction. When they move, obviously we can see current flow in the circuit. So when current flow is there in the circuit, in the sense, it is detected a photo. This is the basic phenomenon. So yesterday we discussed about avalanche photodiode. In avalanche photodiode, there again impact ionization takes place. That impact ionization will not be taking place in this, right? Second point, in the PIN diode, because intrinsic region, the forbidden region is wider. Say, in case of avalanche photodiode, here the forbidden region is confined to this region, this part, N plus NP, here only. Clear? Only this part is active in that case. In the avalanche photodiode, this part is active. Here only we have most of the maximum forbidden gap, right? And the role of this is very less. This part and this part is very less. But whereas in case of PIN diode, see, okay, in this case, here we are taking one material, one type, that is N type. This is P type. So forbidden gap must be in between this. So here forbidden gap width is higher, right? Depletion region width is higher, right? I here in this case, In case of avalanche photodiode, depletion region is present in this region. The width is less. When width is less, obviously the minority charge carriers will be blocked easily. So there is no dark current in this case. Whereas in this case, dark current will be there. Okay. So due to that, when you study VI characteristics, we can see at before incident of any light, you can see some magnitude of current flowing in the circuit. This magnitude of current is due to that minority charge carries, dark current. When light is made to incident, as you increase the intensity, this flow of electricity in the circuit increases because more number of electron holes pairs will be generated. Right? Understood. This is what happening in PIN diode. Yeah. Right. Now let us come to very important another point, another topic. We discussed about dielectric and indielectric, direct and indirect band gap semiconductors and radiative and non-radiative recombinations. We discussed about radiative recombination in direct and indirect band gap semiconductors that we have discussed. In generally, radiative recombination takes place in direct band gap semiconductors, where at zone center k equal to 0, the maximum value of energy of valency band and minimum energy of conduction band is present at zone center, right? So then the electron hole recombination, that electron after its mean lifetime de-excite to lower energy states gives out photon. This is direct recombination, radiative recombination in direct band gap semiconductors. Whereas if you take silicon, it possesses indirect band gap. So what happens there? At zone center, these two energies will not occur. The maximum of valency band and minimum of conduction band will not occur at zone center. They will have some different values, right? So due to phonon release, lattice vibration, then the values will be matched. It recombined with hole. It gives out photon. This is what we discussed in direct and indirect band gap semiconductors. Now coming to non-radiative recombination mechanisms. There are few variations, and non-radiative recombination mechanisms takes place mainly through the defects in the crystals, and it's simple to understand. Extrinsic semiconductor is a defected crystal, remember it, because we are doping foreign atoms into it, right? And while a crystal is growing, actually crystal says a crystal is grown along x-axis. After growing up to some extent, due to some uh, technical reasons or thermal variations or stress, whatever, the growing direction differs little. Practically, if you see crystal with naked eye, you cannot find it, whether how much defect, whether it is defect or defect is there or not. Okay, so due to that, what happens? Boundaries takes place. This is one region. The crystal is grown like this. All the planes are grown like this, and suddenly changed in the direction. So due to that case, say the crystal planes are grown like this. Due to some reasons, the direction of due to some reasons, crystal planes are grown like this. Due to some reasons, they changed the direction of growth. So here what is happening in this region? boundary is taken place like that, and we are substituting the foreign atom, or in some crystals, while crystal is growing on, few atoms will be missed from the crystal, or some trap, some foreign materials will be get trapped in the crystals. Many things are there. These are the centers that act as plays an important role in non-radiative recombination. Okay, so in that, one of the these are the transitions. Don't word upward transitions. That's it. So in this one of the phenomena, recombination at recombination center. Right here, what is happening in conduction band? Electron directly will not go to the valency band and recombine with hole. Okay, the electron will not recombine with hole directly. The electron first go to the recombination center. This is recombination center. Okay, by giving out a phonon. This phonon again will be absorbed by the material. Phonon comes out as heat. It dissipated as heat. Okay, maybe you cannot measure it. And this here, this acts as recombination center. Some defect. Okay, the electron is first reached to recombination center and again reaches to the valency band and recombined with hole. In this case also phonon is released, not it is not radiative recombination. Photon is not released. Photon is not going to emitted in this case. Phonon, lattice vibration. That lattice vibration again converted as heat. Okay, this is called recombination at recombination center. This is one transition phenomenon in non-radiative recombinations. Is it clear? The electron in the conduction band recombined with hole via a recombination center somewhere present somewhere in between. In these two transition case, the energy is released as phonon, not photon, because it is non-radiative recombination. Right. Now, come to this one. See, in this case, in conduction band, electron is present. At this different energy level, positively ionized atom is there. You will get idea now, where in which case we get the positively ionized atom, whether N doping or P doping, N material or P material. Okay, here positively ionized atom traps the electron. Okay, so here this electron is trapped by positively ionized atom. Again, here also phonon is released. Because transition is there between two different energy levels, in the sense some energy equal to that of energy gap must be get released. Here phonon is released. Okay, right. This is transition due to electron trap. Similarly, hole trap. Now you can right. Now here in the previous transition is electron trap. This is hole trap. The hole in the valency band is trapped by negatively ionized atom in any another different energy level. In this case also phonon is released. Okay, one more very important phenomena, very interesting. Okay, see this. This is called Auger recombination. Auger, AUGUR, Auger recombination. Three cases are there. Here I will explain the basic phenomena, what happens in this Auger recombination. Okay. In Auger recombination, the electron in the higher energy state recombined with hole in hole gives out some energy, right? That is not radiative, only energy, but it is not photon. Gives out some energy. That energy will be absorbed by some uh, electrons or whatever, and they get energy, kinetic energy. They collide with, this is called Coulombic collisions, and they collide with another electron. So this emitted energy due to this transition, see, due to this transition, emitted energy is absorbed by another free electrons, free charge carriers, and they raise to the depth of deeper energy levels in that band gap. This is conduction band. Conduction band, deeper energy, this is lowest energy level in the conduction band. Deeper in the sense, you have to go upward. Is it clear? Again, you listen. This electron recombining with hole. In this recombination, energy will be released. This energy is absorbed by free charge carriers. In between, many charge carriers will be there. They absorb and collide. Coulombic collisions it is called. Then this gets energy in the form of this energy, and it is kinetic energy. Due to that kinetic energy, it will be raised to higher energy levels. After raising to higher energy levels in the same band, and its higher energy gives out as thermal energy and comes down, and again occupies its original states. Is it clear? Shall I repeat? Listen again. Very simple. This recombination, electron hole recombination, gives out energy. That energy absorbed by free charge carriers. In between Coulomb collisions, Coulomb energy due to Coulomb collisions, that you remember. Same thing, because that energy absorbed by free charge carriers, they collide each other. Again, any one of the most free charge carriers gets kinetic energy. With that energy, it is raised to the higher energy levels in the same band. After some time, it gives out this energy as heat, thermal energy, and thermalization. Thermal energy it gives out, and gives out as thermal energy, and occupies its original state. This is called Auger recombination. Okay, here I named in the notation is there for these energy levels: HH, LH, SO. HH in the sense heavy whole band. Easily you can understand. Heavy whole band. LH is light whole band. SO is split off band. Right. So coming to second process, second phenomena in the Auger recombination. In the first, in the electron in the conduction band recombined with HH hole in the HH band. Now, electron in the conduction band recombined with hole in the HH band, same phenomena is taking place. Here, energy released is absorbed by electron in the conduction band. Here, energy released may be absorbed by electron in the valency band. That free electron rises to up to some higher energy levels. It will not cross the energy gap, of course. And after some time, it gives out its energy as heat and takes original position. Similarly, here, the electron is recombining with hole. This electron is recombining with hole, right? And the electron in the split off energy levels, okay, is raised to higher energy levels in the valency band. It is raised to higher energy levels in the valency band. Does not cross this energy gap, remember, right? And it gives out energy, its energy, excessive energy as heat again occupies its original states. These three phenomena, these three processes are Auger recombination. Clear? Right? Any doubts? If you have any doubts, you ask me. You can send the doubts via WhatsApp. So today we have discussed about PIN diode and these non-radiative recombinations. Tomorrow we'll discuss about solar cell. Right? Come with preparation and you read it. You have notes. Read it. If any point is not discussed or you did not understand in the notes, you can ask. Okay, you just write a send a WhatsApp message. Tomorrow in the class, first we'll discuss these doubts. Right? Again, be happy, stay at home, be safe. Spend much time with studies. Practice the mathematics and practice this lessons, and you complete the assignments also. Already I have given assignments, complete it, and I will give a mail ID. To that you send the PDF files of those assignments. Okay, right? All the best.